Look at that.
Did that show up?
Yes, looks good.
Okay. Wow. Yeah, well, if there are no more questions for Glenn, I can go ahead and get started here.
Go for it.
All right, sounds like we are all good. All right, so Git. You may have heard the term before if you've dabbled in software development at some point, or maybe you actually don't know much about what it is at all, and that's okay too. If we were in the room together, I was going to do a show of hands, but it's going to be a little bit more tricky in this format. So probably at some point in our lives, we have worked on a project that looks something like this, where you are trying to keep track of multiple versions of something, whether it's a file, a presentation, and you just start renaming it creatively. And then to make things even more worse, it could be a group project and you're emailing something like this around on a daily basis, trying to sync up each other's changes and keep track of what was working and what wasn't. This is bad, needless to say, and we can do a lot better. And the way we're going to do that is by using something called a version control system. Git is an example of one of these systems. And the basic strategy here is that it's going to keep track of your files and the changes between different sort of snapshots in time. Now you keep these changes organized and also collaborate with other people. So Git was designed for tracking source code specifically in the context of software development. It was invented, I believe, in the early 2000s, and it was designed for development of the Linux kernel, to be exact. But it doesn't mean you can't use it and also abuse it for other things as well. And we'll talk about some of those possible use cases in the subsequent slides. But this is a very powerful tool for organizing certain types of files, keeping track of changes, and also collaborating with others by being able to transfer those changes to other systems. Git is not the only one. Probably second in popularity, maybe a Subversion. It has kind of a more dated reputation. Sorry for all the more senior software developers out there. Another one you may have heard of is Mercurial, or just known by HG for short, chemical element. That one is what's used for tracking the source code of Chirp, the radio programming software. Supposedly it can handle binary files a little bit better than Git does. I haven't actually had much experience with it. RCS is sort of a old school Linux lightweight version control system, and there's all sorts of commercial offerings, but you probably wouldn't be using those in a hobby or open source setting. Git definitely remains the most popular choice, and if you were going to learn how to use one of these, I would recommend Git for sure. All right, so going back to Git, let's just address a couple of misconceptions here to get us all onto the same page. So objection number one is, I'm not a software developer. Why do I need to learn this, and why is it useful to me? Well, as we saw in several of the previous presentations, as ham radio is going into the 21st century more and more, software is a huge part of this hobby. You saw how the EOSS guys were making custom tracking systems. You saw all the work that Willem and Chris were doing on Coleman. There's a lot of software development going on, especially with digital mode, software-defined radio. Having some background in this, even if it's just awareness level, can be very helpful, in my opinion. But even if you're not writing software, things like configurations for network equipment or your server, just raw documentation, even KiCad or KiCad, depending on how you want to pronounce it. And one thing I also do with Git is store my code plugs. So I have a version copy of all my radio's code plugs and programming information that I can easily push between computers and also walk back in time if for some reason I need to get back to an older version of them. So there's lots that you can do here. Another objection is, well, it's too complicated for what I need to do. And it is true, Git can be very complicated if you want to dive all the way into it. But at the same time, you don't need to make work for yourself and use a very complicated workflow, right? Like you can just do simple operations with it. And then finally, a lot of people get confused about the difference between Git and, say, a service like github.com. Doesn't this mean that if I use Git, I'm tied to GitHub or GitLab or one of these hosting sites? Does it mean that everything I write has to be public? That is all not true. These are totally different things, and using Git does not require you to make anything public. It's used in commercial closed source software development all the time. So what does Git actually look like? Well, canonical Git is a command line utility. And if you are a software engineer, you're probably going to be more comfortable working with that. But there are also graphical clients that interact with Git. And you can see some examples of those on the right. One of those in the foreground there is actually called Tortoise Git, which integrates with the Windows File Explorer shell. That's actually like a very convenient one if you want to have a still powerful but more user-friendly introduction to Git, because it's right there in your file browser. We're not going to focus on either of these exactly in this session, just because it's a 20-minute talk. We're going to talk only about a couple of Git concepts, so that if this does pique your interest, you'll have a little bit of awareness that'll allow you to jump into an online tutorial or maybe try playing around with some of these things with just enough background to cause some trouble. So starting out, let's say that we have a blank slate here. What's the first thing that we do? Well, Git stores your workspace in what it calls a repository. You're going to see that word referenced all the time. And we create a new repository through what's called initialization, or just init for short. On a lot of these slides, I will be posting the command line invocations for doing a lot of these operations, just for your reference. You can maybe start connecting the dots a little bit. But Git init is what you would run inside your project directory to basically create the brand new Git directory. You can do this in an existing project, or you can start adding files later. It will create a .git directory, and that is where Git stores all of its internal information to track your changes over time. Another common workflow to get started is to actually clone an existing repository. So the git clone command will go out and basically download a repository from somewhere else. We'll talk more about that in a little bit, and plop it onto your hard drive so that you have a local working version of that repository that you can make changes to, and go from there. All right, so commits. This is sort of the basic working unit within Git. A commit is basically a snapshot of your files at one point in time, and they are annotated with an author, date, and a description called a commit message. On the right there, I have a couple of example commits. In this case, the descriptions are like 2 or 3 words. In practice, you should probably be writing at least multiple sentences describing what's happening inside that commit. And you can see that they are identified by a hexadecimal hash. Typically, that algorithm is SHA-1, and it's actually going to be a 40-bit hash, although you can truncate that to a shorter prefix if you'd like. I'm only showing 6 hex characters in this example. And they each point to their parent commit. And that's how you start building a chain, a lineage, basically. So initial commit up there at the top, and then this programmer has added 2 commits beyond that, each representing either a new feature or some other change that they made to their code base. Git show followed by the hash will display a commit if you're using CLI Git. And then git log will actually display representation of this history going back to the beginning of that chain. So when you're creating commits, it's important to remember that by default, Git does not actually track everything inside your workspace. You have to tell it what you want to start tracking. And the things that you do want to track would be, for example, your source code, your documentation, your KiCad project files, whatever you're actually, whatever your project actually is. And then you would avoid tracking things like compiler outputs, temporary or autosave files, stuff like that. That does not belong in a Git repository because it's not your actual thing you're trying to store here, right? It's all side effects and autosave information that is not actually part of your code. And you can sort of automate what should be ignored with a .git-ignore file, make that a little bit simpler. So when we actually want to start building a commit, there's an intermediate process or location called the stage. You don't have to commit everything inside your working directory at one time. You choose what gets incorporated into the commit. And you do that by basically staging files that you want to include in that commit. And on the screen there, you can see the invocation for doing that. Git add is what you would do in command line git, and that will also automatically start tracking the file if it's not already. And then finally, git commit is what you would call in order to actually lock those stage changes in and commit a new commit to your history like this. And also during that commit process, you will have an editor window pop up that will allow you to type that commit message out. And so you can have a good description of what happened inside that commit for your own memory and for the next guy. Okay, so we'll talk quickly about branching. So you may remember from the previous set of slides that a commit can actually have one, sorry, excuse me. Remember that commits point to their parents, but it's possible for a commit to, or for multiple commits to point to a singular parent like this. And this is what's called branching. So up until now, we've been on this default branch that is called main. And what a branch really is just a pointer to a particular location in this graph. Right, so you can see down here that main is pointing to where we left off last time. But let's say, for example, that we want to diverge from this timeline and maybe start working on an experimental feature. We'll call that feature one, and it's a new branch that has its own pointer. And that allows us basically flip-flop between these two. We can check out one of these branches at a time, and it can sort of put away one and pull out the other for you. And this is really useful if you have multiple features or things in progress at one point in time. Because let's say, for example, you're working on this new feature right here on the right side, but you want to demo, the good working code that's over on the main branch to a friend. Well, are you going to go through there and copy and paste all your changes out and try to do that successfully? That's not going to work out for you. But with branching, you can easily swap back and forth. So logically, if we can diverge, we need to have a way to eventually bring changes back together. And that's what the process of merging is called. So what we're seeing here is a merge commit introduced at the bottom that actually points to two parent commits at the same time, reflecting that this commit inherits changes from both of these lineages and puts them together such that we can continue building off from that bottom commit with more changes, incorporating everything that has come from before it. Now, as you may have guessed, it is possible that we have conflicts when we are doing this operation, right? Because it's possible that the two commits that come before the merge, blah and more code, please use more descriptive commit messages in that in actual use. But it's possible that both of these changed, the same section of code, and now they don't easily come back together again. And when that happens, Git will actually ask you to manually resolve what's called a merge conflict. Once again, you're going to have to go back to your editor. You're going to have to sort out which pieces you want from where, and then basically recommit those changes to sort out that problem. There is an alternative strategy called rebasing that's also used for incorporating changes from another branch. In this case, it's more of a replay-based mechanism. I'm not going to go into depth on that right now, just in the interest of time.
4 minutes.
Oh boy. So last sort of Git feature I want to cover is the idea of remotes. So as I mentioned earlier, Git can be used to send and receive your changes to other systems, and that is basically the foundation of collaborating using Git. So over HTTP or SSH, you basically instruct Git to send commits over to some remote system. Now this is where GitHub, GitLab, Bitbucket, all these repository hosting providers come back in. This is typically what would be your remote in your Git repository and the place that you send changes to in order to distribute them to other people or even just to back them up. This is a great place to host your code securely. And these commands are the commands that you'll probably be using to do these operations. So let's talk real quick about the value that these providers can provide to you. So if you're working with multiple people, this can provide sort of a hub, sort of a primary location to store your repository that other people can clone from, and then also push their changes back up to when they want to contribute something back. There'll often be a web front end for doing the code. You definitely have seen this before on github.com, for example. It'll also provide a bunch of collaboration tools, such as an issue tracker for basically managing the project side of software development. Automatic build systems could be incorporated to basically run tests on your code regularly or test compile them. Access control, so you can control who has permission to see or commit things to your repository, and also enforce things like pull requests for making changes. And then frequently another feature you'll see is called forking. It basically allows you to take somebody else's repository on GitHub or GitLab or whatever, make a copy of it that you can then work on in case you don't have permission to work on the original. Then, of course, the pull request and merge request, depending on how you want to call it. This is a procedural tool for incorporating changes from somebody else's repository back into your own. It'll lay out all the changes, and then you can comment on it and basically have an approve or a denial on whether or not you want to take in that code. If you're working solo, you probably won't be doing forks and pull requests, but if you're going to contribute to an open source piece of software, that's definitely something that you're going to have to get very well versed in. And just a quick diagram of how a flow like that would work. This is a random repository I just took from the RMHAM organization that I think Chris has worked on. If you wanted to contribute changes to this, you would start off by forking it so that you have basically your own addition to this repository. And then you would clone and push stuff back from your working copy on your PC. And then if you want to incorporate those changes back in to upstream, that's where a pull request would come in. So I know I covered a ton of information in these 20 minutes, but hopefully this will at least give you some of the terminology or background such that you can go ahead and try out a more in-depth tutorial online, or read any of the large volume of guides and information that's available out there, and see if you can use Git in your own life to organize your software projects or documentation, or even jump into collaborative open source software development.
Roger W3MIX says you might want to mention the boxes are moving down the page with each commit, but each commit has a pointer so the previous or to the previous version. So arrows don't designate the flow.
That is right. So in this example, which I think is what he's talking about, yes, as we're going through time, we're actually going top to bottom here. But the way that a commit is structured internally is that it points back to its predecessor. So yeah, thank you for pointing that out. That definitely clarifies this diagram a little bit more.
You have
the reason it's like this is because we're building, commit after commit after commit, and so we don't want to have to modify a previous commit to tell where it's going next. Much easier to have a new commit that says where it came from.
It's also super useful for instances where you have just completely DFIU'd the code,
Yes.
and now you need to roll it back to the last working version. That saved my buttons several times.
Absolutely. I mean, Git is so valuable just in reducing the chance of you screwing something up horribly. As a general rule, if you have committed something in the past, you can probably get it back somehow. As long as you don't prune your tree, you can cause a horrible situation, but probably still recover from it.
It's recorded. You should be. I can go back to it. Steve said. So yeah, it's good.
All right. Any other questions for Tristan?